So in the last video, we learned the power rule, the first of the major rules that we're going to learn in section 3.3. And as interesting as I think it is, and as much fun as it is to go through all these steps really slowly, I ended up spending almost a half an hour going through the first 2 pages of this layout, which has 14 pages in it. So in the interest of time, I should probably speed things up a little bit and maybe not go in quite as much detail as I did last time. The big takeaway from last time was this thing called the power rule. It's written right here. It says that anytime you're taking the derivative of x raised up to some number n, more on that number later, the derivative is just the product of that number n and x raised up to 1 less than that number n. It might be easier just to remember some example like the derivative of x to the 24th is 24x to the 23rd. That's the power rule. But what if you weren't just asked the derivative of x to the 24th power? For example, what if you were asked the derivative of x to the 5th power plus x to the 4th power? I mean, we know the derivative of x to the 5th power, and we know the derivative of x to the 4th power, right? Each of those individually, we can use the power rule on. The derivative of x to the 5th is just 5x to the 4th. The derivative of x to the 4th is just 4x to the 3rd. But the question is the derivative of x to the 5th plus x to the 4th equal to 5x to the 4th plus 4x to the 3rd? Is it true that the derivative of a sum is just the sum of the derivatives? Because it would be really nice if it was. Make problems like this pretty easy. Turns out that yes, it is, which is awesome. I won't prove this to you in detail, again, because of the time shortage thing, but it really turns out to just be an algebraic argument. I mean, imagine if you were taking the derivative of this function. If we call this thing f of x, so f of x is x to the 5th plus x to the 4th, then using the difference quotient, we need to know f of x plus h, which would be x plus h to the 5th plus x plus h to the 4th. And then from that, we'd have to subtract f of x, which is this x to the 5th plus x to the 4th thing, and then we divide that entire mess by h. Rather than try to simplify this thing down so that I can take the limit, let me just rewrite this thing. Let me take this negative sign and distribute through the parentheses, and then collect the terms in a slightly different order. If I distribute the negative sign, this becomes negative x to the 5th and negative x to the 4th. So I'm adding up 1, 2, 3, 4 things, 2 of them being negative, 2 of them being positive. And you can add in any order you want because addition's commutative. 3 plus 7 is the same as 7 plus 3. So maybe I'd take this x plus h to the 5th and add this negative x to the 5th, that's this part, and then add this x plus h to the 4th and this negative x to the 4th, that's this part right here, divide the whole thing by h. But if you think about this as these two terms plus these two terms divided by h, you could rewrite this as the sum of these two different fractions, right? I mean, maybe it's more comfortable for you to go in this direction than this direction. But if you started out on the bottom here, you'd recognize you have a common denominator. So the way you'd add these two fractions by adding up their numerators and writing the denominator once, and that would give you exactly the line that you see right here. What I'm saying is using the difference quotient on this expression as f of x produces this expression that you see down here. The limit as h approaches 0 of this mess plus this mess. Do you remember a few sections ago, the very last video when I tacked on these things called limit laws, and I said that eventually it'll be useful to know these limit laws? And one of those limit laws said that if you're taking the limit of something plus something else, you could rewrite that as the limit of the first thing plus the limit of the second thing. You remember that? Maybe, maybe not. It doesn't matter. It's a thing. I told you about it. Because of the limit laws, we're allowed to go from this bottom line on the left to this top line on the right. Why is that important? Because look at what we produced. Look at what we have in this red box right here. The limit as h approaches 0 of x plus h to the 5th power minus x to the 5th power divided by h. Do you recognize that thing? That is exactly the derivative of x to the 5th power. Think about it. If someone asked you the derivative of x to the 5th power, you'd be like, difference quotient. Limit as h approaches 0 of f of x plus h to the 5th power, minus f of x to the 5th power, divided by h. You'd write exactly this box. This box represents the derivative of x to the 5th power. And similarly, this box right here represents the derivative of x to the 4th power. So even though we haven't actually calculated these derivatives, we've rewritten the original question as a different question which we can interpret. This original question was the setup for the derivative of x to the 5th plus x to the 4th. Playing the role of the function was the sum of those two terms. We algebraically manipulated it to make it look like this because this is the derivative of x to the 5th plus the derivative of x to the 4th. And these are two things we know how to figure out. What I'm saying is, sure enough, the derivative of x to the 5th plus x to the 4th is just the derivative of x to the 5th plus the derivative of x to the 4th. If somebody asked you this question right here, you'd be like, easy, it's just equal to 5x to the 4th plus 4x cubed. That's called the derivative sum rule. And the great news is it's not dependent on x to the fifth and x to the fourth. These same algebraic steps will work no matter what function you have right here and what function you have right here. You could copy every single one of these steps except change all the references to x to the fifth power into, I don't know, f of x, and all the references of x to the fourth power into g of x. And what you would be doing is proving that the derivative of a sum of two functions, f of x plus g of x, is the exact same as the derivative of the first function, f of x, plus the derivative of the second function, g of x. This is a little bit annoying to write because of all the parentheses, so there's a nice little shorthand that people commonly write. Instead of f of x, they just write the letter f. It's implied to be a function, you don't need the of x. Same logic with the g, f plus g. Instead of saying the derivative of in the parentheses, because that's a lot of writing, we can just put this little prime up here and assume that this means the derivative of the stuff inside the parentheses. The left-hand side of this equation can be rewritten like this. The right-hand side, the derivative of f of x, is just f prime of x, or just f prime if we're leaving off the x's for shorthand. Similarly, the derivative of g of x would be g prime of x, or just g prime if you really want to shorthand stuff. The second of our rules is called the derivative sum rule, and here's one way that you can write it. It's really nice. That's not the only rule we're going to tackle in this video. What if we were asked the derivative of 10 times x to the fifth power? The problem down here is we're not adding stuff up, we're instead multiplying stuff. We're multiplying some function x to the fifth power times some constant, the number 10. Well, what we could do is treat the inside here like some function, f of x equals 10x to the fifth power, and then put it into our difference quotient. The limit as h approaches 0 of f of x plus h minus f of x divided by h, and simplify it forever and see what happens. You know what we'll end up being able to do? We'll end up being able to write this as the limit as h approaches 0 of 10 times x plus h to the fifth power minus x to the fifth power divided by h. And then I'll be like, remember those limit laws? And you'll be like, no, I don't, but I could page back a few pages in my notes and find them. And I'd be like, cool, look at those, because in your limit laws, you saw that when you're taking the limit of the constant multiple of a function, that's just equal to that multiple times the limit of that function. This line, which just trust me, you'd get if you algebraically manipulated this expression in the same way we did up here. If you're really interested, try it on your own. I bet you could figure it out. Thanks to our limit laws, is just 10 times this expression. And much like above, this expression is something that we recognize. This expression in blue is the derivative of x to the fifth power. So what we're saying is that the derivative of 10x to the fifth power is just 10 times the derivative of x to the fifth power. Note that we're just taking the derivative of the x to the fifth, not the 10. The 10 is written before this verb, which means take the derivative of the parentheses. Up here, I still need to take the derivative of the 10. I'm taking the derivative of this entire thing. But what this constant multiple rule is telling me is that when you're taking the derivative of something like 10 times x to the fifth power, you can rewrite that as 10 times the derivative of x to the fifth power. And as long as you know the derivative of x to the fifth power, which, by the way, you do using the power rule, it's 5x to the fourth power, then you're able to answer the original question. My final answer here would be something like 50x to the fourth power is the derivative of 10x to the fifth power. More generally speaking, this constant multiple rule tells me that if I'm taking the derivative of a constant times some function f of x, that's equal to the constant times the derivative of that function f of x. This is how most books would write your constant multiple rule. I find it a little bit unattractive with so many parentheses in there, kind of hard to look at. It would be nice if there was some sort of shorthand that we understood that we could write to represent this rule. Something like c times f, where implied was that f is a function and c is just some constant number. This little prime up here could mean we're taking the derivative of the entire thing, and we could say that's equal to the constant, no prime here, times the derivative of the function. Much like we can shorthand the derivative sum rule, we can shorthand the constant multiple rule like this. That's the third rule in this section and the second of this video, and it's a really useful rule, this constant multiple rule. We're going to learn 2 more rules in this video, but they're really quick. They're kind of minor rules. Sometimes I don't even write them down. What if my function was really boring, if it was just f of x equals x? Could I figure out the derivative of this function? Well, I mean, sure, you could. You could throw it into the difference quotient or the definition of the derivative and see what happens when you simplify, but you don't even need to. You can prove this derivative that it's just equal to 1 with pictures if you want, which is kind of cool. Think about the graph of f of x equals x. When I put 3 into this machine, 3 comes out of this machine because the output is the same as the input, the letter X. Goes through this point right here. And when I put 2 in, 2 comes out, and 1 in, 1 comes out, and 0 in, 0 comes out. In fact, maybe you can look at this and think about it as y equals mx plus b, playing the role of the b as a 0, playing the role of the m as a 1. The graph of this function is just this diagonal line that has a slope of 1. Think back to what the derivative means. The derivative is just a formula that tells you the slope of your function at any x value. But for this specific function, because it's linear, the slope of the tangent line to this graph is always going to be the exact same. Tangent line to the graph is just the graph in this case because my function's linear. And because the graph has a slope of 1, the slope of the tangent line to the graph at any point would be equal to 1. What I'm saying is the derivative of this function, x, is just equal to 1. A similar visual argument will tell you that anytime you're just taking the derivative of a constant all by itself, that's equal to 0. Why? Because you're going to think f of x equals some constant. I don't know, 4. Sure. What's the graph of f of x equals 4 look like? What this is saying is no matter what x you put into this machine, what comes out of this machine is the number 4. So you want to put negative 7 into this machine? Sure, go ahead. What comes out is the number 4. Same as when you put negative 1 into this machine, or 0 into this machine, or any other number. The graph of f of x equals 4 is a horizontal line with a height of 4. Can you think of a machine that would give me the steepness of this graph? It would tell me the slope of the tangent line to this graph at any point. Well, what would a tangent line look like? Again, it's linear. So the slope of the tangent line would be the same as the slope of this line. What's the slope of this line? It's horizontal. The slope when you have a horizontal line is just 0. This graph goes up 0 units each time it goes 1 unit to the right. Because this linear graph has a slope of 0, the slope of the tangent line to this graph would be 0 for any value of x. So the function that tells me the slope of the tangent line at some point x, in other words, the derivative of this function is just equal to 0. Nothing special about 4. This would happen for any constant. Before I end this video, I want to do a quick example for you, because it's going to put together all of the different rules we learned in this section. The derivative sum rule, very important. The constant multiple rule, very important. The fact that the derivative of x equals 1, you're just going to kind of memorize that. And the fact that a derivative of a constant all by itself is equal to 0, again, not super important. With those 4 pieces of information, we could take the derivative of any polynomial we want. And it is much, I know I capitalized this, but I feel like that should be boldface and underlined too. Much easier than it was before. Don't believe me? Take this example back to 3.1. Throw that into a difference quotient and try to simplify this huge mess. You don't even have to do the whole thing. Do the first few steps and you'll be like, yeah, you were right. Never mind. I never want to figure this out with the difference quotient again. You don't have to. The derivative of 8x to the 5th plus 3x to the 4th minus 2x cubed minus x squared plus 4x plus 21 is easy. Let's first use the derivative sum rule. That says when I'm taking the derivative of things being added together, I can instead just take the derivative of each term individually. So I got the derivative of 8x to the 5th plus the derivative of 3x to the 4th plus the derivative of negative 2x cubed plus the derivative of negative x squared plus the derivative of 4x plus the derivative of 21. Using my derivative sum rule, like 5 times or so, I can rewrite this derivative as this derivative. That's good news. On the one hand, I've changed one problem into 6 problems, but on the bright side, that one problem was really hard, and each of the 6 problems isn't that bad. What would I do next? Now I can use the constant multiple rule. In fact, I can use that a bunch of times. The derivative of 8x to the 5th, that's a lot like this derivative of 10x to the 5th that we already did. That's just 8 times the derivative of x to the 5th power. Same logic here. The derivative of 3x to the 4th is just 3 times the derivative of x to the 4th power. The derivative of negative 2x cubed is negative 2 times the derivative of x cubed. So I have plus negative 2 times the derivative of x cubed. Instead of plus and negative, I can write minus. So I got minus 2 times the derivative of x cubed. Same logic here, thinking about this as negative 1 times x squared. I got minus 1 times the derivative of x squared plus 4 times the derivative of x plus the derivative of 21. What we've done is rewritten this original problem in a form that we can evaluate all the different derivatives. Oops, it looks like I wrote 4x instead of x to the 4th here. Let me fix that real quick. Hopefully you caught that on your own and were like screaming at your screen. Anyways, let's evaluate this derivative. The derivative of x to the 5th power is 5x to the 4th power. So what I have here is 8 times 5x to the fourth power. Similarly, the derivative of x to the fourth power is 4x to the third power, so I got 3 times 4x to the third power. From this next term, I get negative 2 times 3x squared. From this next term, I get negative 1 times 2x. And then for this term, remember the derivative of an x all by itself, thinking about this example, is just equal to 1. So I get 4 times the number 1. And then this last term is the derivative of a constant, the number 21. And we know that the derivative of any constant is just equal to 0. So I get a plus 0 right here. I can clean things up a little bit. 8 times 5 is 40. So I got 40x to the fourth plus 12x cubed minus 6x squared minus 2x plus 4. The derivative of this horrible looking polynomial is now super doable by following through these steps. In fact, I bet a lot of you could go straight from here all the way down to the end in one step. I'd advise against doing that, at least right now. You want to be able to show these steps because if you make little mistakes, it'll be a lot easier to follow your progress and give you partial credit. However, I'm not saying you always have to show every single one of these lines. I think it's pretty reasonable to go from this line straight down here to use your derivative sum rule and your constant multiple rule in a single step, right? Take this 8, write it down in front, times the derivative of x to the fifth, plus 3 times the derivative of x to the fourth minus 2 times derivative of x cubed, and so on. I don't know that you need to show this first line unless it helps you. From here, could you go straight to the end? Probably. I'd probably advise when you're still learning this to do this in 3 steps, 1, 2, and 3. But it won't be long before you cut out this step also and maybe go from here and then straight down to here. And that's fine too. Realistically, in a week or two, you're going to go straight from this to the very end. Just be careful doing that too quickly. Not just for the partial credit in case you make mistakes, but because it's a good habit to really show these different lines, to think about which rules you're using from one line to the next. Because what you'll see is right now, we don't have very many rules, so it's fairly obvious. But as we get into more complicated examples, when we're using more complicated rules, it'll be a lot more challenging. So developing good habits early on is not a bad idea.